Cable bus. Introduction. Cable bus connections have been in service for many decades in the United States. This concept was first developed and accepted by utilities in the United States. It was later adopted by Canada, Japan, Korea, Taiwan, Saudi Arabia, and several other countries. Cable bus was introduced in Article 365 of the National Electrical Code in the year 1969 and later moved to Article 370 in 2002. NEC 2011 describes cable bus as follows. Cable bus is an approved assembly of insulated conductors with fittings and conductor terminations in a completely enclosed ventilated protective metal housing. Cable bus is ordinarily assembled at the point of installation from the components furnished or specified by the manufacturer in accordance with instructions for the specific job. The assembly is designed to carry fault current and to withstand the magnetic forces of such current. Cable bus is an organized method of spacing single-core cables of different phases and locating them inside a well-ventilated enclosure to meet the specification parameters of a connection. Cable bus is manufactured for a wide range of installation up to a rated voltage of 72 kV and a rated current of 8 kA. Cable bus has been tested for a short time rating of 100 kA, RMS. A single connection can have up to 27 cables, 9 per phase, sharing the load. It is the simplicity in design with the least number of accessories and robust construction that makes cable bus an extremely reliable product. The adoption of the cable bus system for a project is a matter of preference of the project authorities. Barring a few applications such as generator connections, a low or a medium voltage connection can be made either with bus duct or cable bus. Cable bus carries only those cables that are associated with a specific connection and is often mistakenly compared with cables running on cable trays. Cable trays are supporting and clamping devices for a wide range of cable connections that do not have a specified rating. Some of the key features of a cable bus are: cable bus usually does not have a conductor joint between the connected equipment. However, a joint may be deliberately introduced for a tap-off connection. Cable bus connections are maintenance-free. Cables in a cable bus connection are immune to moisture and corrosive gases in the atmosphere. Consequently, anti-condensation heaters with associated wiring, thermostat or hygrostat for sensing and control, breathers, and drains are not needed. Cable bus also does not require hot air blowing for removal of moisture before commissioning or charging after a long period of disconnection. Cable bus connections are more flexible and easier to negotiate at the site, which lends itself easily to modification at the site to cater to mismatch or misalignment. Cable bus can run in trenches and avoid right-of-way. Transposition is not required to minimize voltage unbalance and voltage drop, as it can be achieved by cable configuration, interleaving. Compared to a bus duct, a cable bus has a shorter lead time to manufacture and deliver at the site. A cable bus has a much higher current rating than the same number of cables laid in a tray or a conduit. Description: a cable bus connection of a specific cross-section comprises an assembly of standard modules comprising straight section, elbows, tap-off boxes, bends, expansion joints, termination boxes. Cables with several accessories are supplied that are assembled at the site, comprising cables in drum, wall and floor seals, cable jointing and terminating kits, ground conductor, fire stops, hanger, floor and wall supports. Enclosure: a cable bus is manufactured in standard sections. The bottom-most support blocks are fixed at works. The earth conductor fixing clamps are installed at regular intervals not exceeding 1,800 mm, 6 feet. The section length will depend upon the layout and ease of installation. Long straight sections are preferred for outdoor locations since they are economical to manufacture, transport, and install at site. The maximum length of the indoor section will depend upon the constraints of movement. Single section lengths up to 7.5 meters, 24 feet, have been installed. The enclosure is usually made of aluminium sheets and extrusions. The side rails are extruded from aluminium alloy 6061 T6 or 6063 T6. The side rails take the total load of the conductors and the support block. For indoor installation, the top and bottom sheets are punched to facilitate the cooling of conductors, cables, by natural convection. The preferred width of the punch slot is 6 mm, 1/4 inch. In the case of outdoor installation, the top sheet is plain or louvered to prevent direct sunlight, rain, and snow from falling on the cables. The top sheet can also be sloped to prevent the accumulation of snow and wash off the accumulated dust. The aluminium sheets and extrusions can be anodized or powder coated with epoxy paint for additional resistance to corrosion. The preferred thickness of the aluminium sheet is 3 mm, 1/8 inch. In certain, extremely aggressive corrosive atmospheres, the enclosures may be fabricated from stainless steel SS304 or SS316. This will, however, be expensive. Enclosures can also be made from hot-dip galvanized after fabrication, HDGAF, steel sheets. It is preferable to install stainless steel, grade SS304, fixings for all assemblies of cable bus. Conductor. The cables are single core with either copper or aluminium conductors. For the low voltage system, cross-linked polyethylene, XLPE, cables are preferred over polyvinyl chloride, PVC, cables because of their superior properties. For the medium voltage system, shielded, ethylene propylene rubber, EPR, cables are preferred over shielded cross-linked polyethylene cables. The basic insulation level of the cable shall be the same as that specified for a cable bus system. Support block. Support blocks are usually made of maple wood, glass-reinforced polyester resin, SMC or DMC, polyester glass laminated sheets, GPO3 to NEMA, or high-density polyethylene, polyamides, among others. Cable bus of high ampacity can incorporate up to 27 cables arranged in a matrix of 3 rows and 9 columns. An anti-tracking coat may be applied on the surface of the support block if deemed necessary. Maple wood shall be seasoned and coated for protection against ingress of moisture and attack from fungus, insects, and retard fire. Most industries try to reduce the inventories by standardizing on a minimum number of sizes of cables. This reduces the types of different sizes of slots. The space between the two slots is equal to or marginally more than the diameter of the slot. In most configurations, the top and bottom support blocks are identical with slots only on one side. For the intermediate support blocks, the slots are on both sides. The support blocks assemblies are slid into a channel and held in position, with respect to each other, with stainless steel tie rods. This feature provides flexibility for axial movement and alignment of cables. Manufacturers standardize on different types of support blocks depending upon the diameter of the cable, slot diameter, and the number of cables, number of slots. The design of the slots will determine the spacing. The distance between the adjacent sets of support blocks defines the span and is determined by the specified short-circuit current withstand capability. A maximum spacing of 900 mm, 36 inches, for the horizontal run and 450 mm, 18 inches, for the vertical run is the industry norm. Fire stops, wall and floor seals. When a cable bus passes through a wall or a floor, it needs to be sealed for water and moisture ingress. Precaution may be taken to ensure that cables are not accessible at the floor opening by providing a perforated steel enclosure for a height of 6 feet and a bund around to prevent water from stagnating. A metallic frame, steel, stainless steel, or aluminium, of suitable size is installed at the interface. Sealing can be achieved by providing a non-magnetic seal plate with cable glands or with plug seals. Plug seals cater to a range of diameters of the cables. Cable ranging from a diameter of 3 mm, 1/8 inch, to 99 mm, 4 inches, may be covered by 7 sizes of plugs. Fire stops may be provided, if specified. The fire stop for a cable bus differs from that installed in a bus duct since the cable is already insulated for the rated basic insulation level. Expansion joints. Expansion joints may be provided to isolate vibrations and compensate for minor misalignment in layout. They are located across a building expansion joint. Most of the bellows are made of either neoprene or EPDM, ethylene propylene diene monomer, rubber. Terminal adapter boxes. Most often, a cable bus will terminate on transformers located outdoors or switchgear located indoors. Termination adapter boxes shall be made of the same material as that for cable bus. They shall have a minimum degree of protection of IP55. Tin or silver-plated copper adapter plates may be installed at the terminals for interfacing with the cables from the cable bus. Non-magnetic gland plates with cable glands will seal the terminating cables. Often, the outdoor end can be directly terminated onto the outdoor bushings of the transformer. Care should be taken to ensure that the outdoor cable terminating kit meets the requirements of the service condition. For outdoor transformer termination within a cable end box, it is preferable to adopt a horizontal entry for better weather protection. Tap-off boxes. A tap-off connection facilitates diversion of part or whole of the power from the main connection to another branch. It comprises an enclosure with rigid bus bars supported on porcelain or epoxy insulators with rated current and basic insulation level, compatible with that of the cable bus, and shall have a minimum degree of protection of IP55. The material of the enclosure for cable bus rated above 2000 amperes shall be of aluminium alloy to reduce the induced losses. Non-magnetic seal plates shall be provided for the incoming, outgoing, and tap-off cables. Anti-condensation heaters may also be installed if required. Cable joint and terminating kits. Cable joint and terminating kits are usually purchased items and include 2-hole type cable lugs, earthing lugs, stress reduction cones, heat shrinkable sleeves, and high tensile steel galvanized or silicon bronze fasteners. Adapter plates on the equipment shall have a drilling pattern to suit the cable lugs supplied by the cable bus manufacturer. Ground conductor. In most installations, aluminium enclosure acts as a ground conductor. It is sufficient if the enclosure is grounded at each end and at regular intervals to the station earth grid. Many manufacturers claim a continuous current rating of 1000 amperes to 1500 amperes for the enclosure with a temperature rise not exceeding 40 degrees Celsius, 104 degrees Fahrenheit. The resistance of the splice plate joining the sections of the cable bus is maintained at less than 50 microohms. Some projects specify a requirement of an external earth conductor running along the entire length of the cable bus. Stranded bare, copper conductor, tined or plain, of the appropriate cross-section is supplied on reels, and the same is fixed by special cast copper clamps bolted to the side rail. Clamps can be located at an interval of 900 mm, 3 feet, approximately. Hanger, wall and ground supports. The cable bus products are light and are supported by hanger rods from the ceiling or brackets from the wall for the indoor sections. It is the industrial norm that the support span should not exceed 6 meters, 20 feet. Outdoor sections are supported on standard T or H frames depending upon the elevation of the run. Cable bus shall not be considered as a structural member. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the founder-director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.